Here's our last related rate type of problem. We're going to do the rocket problem. So here it is. A rocket is launched so that it rises vertically. You can see that in the picture below. A camera is positioned on the ground 3,000 feet from the launch pad. Again, you can see why that 3,000 is there because our launch pad is like right here. All right. When the rocket is 2,000 feet above the launch pad, its velocity is 500 feet per second. Find the necessary rate of change of the camera's angle at that time so that it stays focused on the rocket. So we're trying to figure out how should this angle be moving so that it stays focused on the rocket. So let's write down our variables. So first of all, we have a camera is positioned on the ground 3,000 feet from the launch pad. So that's going to be an x equals 3,000. When the rocket is 2,000 feet above the launch pad, so when y equals 2,000, we know that the velocity, which is a rate, feet per second, is 500 feet per second. So this rocket is going up at 500 feet per second when y is 2,000. How do we write that? We're talking about the rocket going up at a certain rate. So that would be dy dt. That's how much y is increasing with respect to time. So dy dt when y is 2,000 is going to be 500 feet per second. Now it wants us to know we want to find out the rate of change of the camera's angle. So we're actually looking for d theta dt. We're trying to figure out at what rate should our angle go up to follow this rocket. So what we want to do is we want to use our dy dt, we want to find d theta dt, we want to use this x and y value. So what equation could relate a theta, an x, and a y here? Or a theta, the opposite right here, right? Isn't that the opposite of theta? Just as a reminder, opposite goes across. And then we've got our adjacent, which is this one. So how can we write an equation with theta, the opposite, and the adjacent? Well, you should have used SOHCAHTOA, and you should have said tangent. So we've got tangent of theta is equal to opposite over adjacent, in this case, y over 3,000. Now I know that we're given y and it's tempting to plug in 2,000, but you're not going to want to do that yet. And I'll explain why in a second. Next thing we're going to do is we're going to solve for y. So we're going to multiply by 3,000. So I get 3,000 tan theta equals, well, that cancels, just y. Next step is going to be to take the derivative. So taking the derivative of a 3,000 tan theta, well, that's going to give me a 3,000 secant squared theta, and then don't forget to tack on your d theta dt. And what's the derivative of y? Well, that's going to be dy dt. As a reminder, we're taking the derivative with respect to time. Okay, so why didn't we plug in the y as 2,000? Because, well, we wanted it to be y so that when we took the derivative of it, we get a dy dt, which we have. We have dy dt is 500. So we have 3,000 secant squared theta d theta dt equals 500. We're in really good shape right now, except we don't have secant squared theta. As a reminder, secant theta is the reciprocal of cosine. Well, if cosine is adjacent divided by hypotenuse, then secant is going to be hypotenuse over adjacent. And similarly, secant squared theta is going to be hypotenuse over adjacent squared. Okay? Well, the bad news is we don't actually have the hypotenuse, but we could solve for it using Pythagorean theorem. We've got our x is 3,000, our y is 2,000. Let's do Pythagorean theorem. That's going to be 2,000 squared plus 3,000 squared equals hypotenuse squared. Get that answer and then square root it. and I get that the hypotenuse is 3,605.55. And you should check that yourself. You guys can do Pythagorean theorem. All right, so now we know that what h is, and I'm going to write this over again just to save myself for some room here. I know that my h, or my hypotenuse, is going to be equal to 3605.55. Okay, so let's go back to this formula right here. What is secant squared theta? Well, secant squared theta is going to be the hypotenuse, which is this, divided by your adjacent, which is this. See how I say adjacent here? So we're going to have 3,000, and then I'm going to have my secant squared, which is going to be hypotenuse of 3605.55, divided by my adjacent. Well, my adjacent is 3,000 squared, because remember it's secant squared, d theta dt, and that's equal to 500. All right, we're really close now. I do this in my calculator, and I get 1.44. So doing this whole thing right here, that gives me 1.4444. So I have 3,000 times 1.44444 d theta dt equals 500. Okay, now I need to solve for d theta dt, so I'm going to divide by this 3,000 times 1.444 on both sides. And make sure you put parentheses when you're doing this division. So 500 divided by parentheses, all of this. Okay, so I get a d theta dt is equal to 500 divided by 3,000 times 1.444. I get 0.115, and this is going to be radians per second. Now that's a pretty unsatisfying answer. So if you want, you can go ahead and you can convert that into degrees. And to do that, you would take 0.115 and you would multiply it by 180 over pi. Remember, that's how you convert radians to degrees. So doing that, I get 6.61 degrees per second. So think about that camera has to go up 6.61 degrees per second. All right, if you feel comfortable just watching that one problem, you're totally welcome to move on. I just want to do this second problem for those of you who feel like you need to see this a second time. And I will do it faster, just because I kind of explain every step there. All right, so we have the same exact situation here. We've got a rocket being launched up. Okay, the camera is 4,000 feet from the launch pad. Okay, and then we have, so that's x equals 4,000. We know when the rocket's 1,500 feet above, so that's y equals 1,500. Its velocity, or dy dt, is equal to 750. Okay, we're looking for the rate of change of the angle, so we're looking for d theta dt. And we know actually that we're going to have to find the hypotenuse, and so I'm going to put a question mark there. So let's just go ahead and find that hypotenuse first. Just real quickly, let's do some Pythagorean theorem. So this would be your 4,000. You're told that the rocket height is 1,500. So do Pythagorean theorem with that, and I get that your hypotenuse is equal to 4272. And you should confirm that, folks, because we've got to make sure we know the Pythagorean theorem. You can always double check this by saying, is this bigger than those two numbers? Because we know the hypotenuse is the largest side. All right, let's go ahead and let's set this up. This is going to be tangent of theta is going to be opposite, which in this case is y, over our adjacent, which is 4,000. Okay, let's multiply by 4,000 on both sides. Okay, I get 4,000 tangent theta is equal to y. Now let's take the derivative of both sides. So I get 4,000 secant squared theta d theta dt equals dy dt. Okay, now let's find secant squared theta. Okay, so this is going to be 4,000. Secant squared theta is going to be hypotenuse, which we know is 4272. We know our adjacent, remember this is h over a squared. My adjacent is going to be this 4,000. I have to square it because it's secant squared. D theta dt is equal to dy dt. Well, dy dt we actually already know is what? Where is that? 750, so I can plug in 750 there. All right, so what's kind of cool in this problem is the 4,000s cancel. Actually, that's not true, right? Because we've got squared. Silly goose of a Miss Sorensen, eh? So let's just go ahead and find this answer first. We get 4272 divided by 4,000. Square that. That gives me a 1.14. So I get 4,000 times a 1.1406 equals 750. Okay, next step is going to be to divide by this whole mess. Okay, don't forget your 1.406. Okay, and what do we get? 750 divided by, and make sure you put parentheses here if you're going to do this all in one step. So 4,000 times. I get that, I missed my d theta dt, I'm Russian, sorry. My d theta dt is equal to 0.1333, and that's going to be radians per second. If we want, we can go ahead and convert that into degrees by doing 0.133 times 180 over pi. And that gives me 7.64 degrees per second. I know this is difficult, folks, but we can do it. We're going to do plenty of practice, and these problems won't change. They won't look any different. Thanks for watching.